In this lecture, we will go ahead and understand a very important concept in linear programming, which is related to simplex method. And what we are going to do today is basically known as primal to dual conversion. Okay. Follow with me step by step. This might become a little confusing otherwise. So first of all, we are going to go ahead and understand what are the steps involved. Let's take a question. So for example, I'm talking about maximizing z is equal to x1 plus 2x2 plus x3. And I'm saying subject to 2x1 plus x2 minus x3 less than equal to 2 minus 2x1 plus x2 minus 5x3 greater than equal to minus 6, 4x1 plus x2 plus x3 less than equal to 6, x1, x2, x3 greater than equal to 0. Now there are a lot of steps involved in this. So step 1, convert the problem in canonical form. What does it mean to convert the problem in canonical form? To convert the problem in canonical form means, see, if it is min, then you will keep min with all the constraints greater than equal to. If it is a max, you will keep max with all the constraints less than equal to. This is how you can convert this into a canonical form. So if I have this function and I have to write this in the canonical form, please see this. I am maximizing, right? It's a max function. So max z is equal to x1 plus 3x2 plus 2x2, sorry, plus x3 subject to. Now I have to see, because it is a max function, every constraint should be less than or equal to. So the first constraint that I see is already less than equal to. So I will write the constraint as it is 2x1 plus x2 minus x3 less than equal to 2. Now go to the second constraint. Because the second constraint is greater than equal to, I will convert this constraint in less than equal to. And from inequalities, we know that how can we change the constraint? We can convert the constraint by multiplying with -1 throughout. So if I multiply my equation with -1 here also and here also, my equation will become 2x1 minus x2 plus 5x3 less than equal to 6. And since the third constraint is correct, it's already in the right format, I will write it as it is. 4x1 plus x2 plus x3 less than equal to 6, x1, x2, x3 greater than equal to 0. So we have converted the entire into the canonical form. Second, after you have converted everything into the canonical form, the second step is change the objective function of maximization in the primal into minimization in the dual and vice versa. So if it is a max initially, then its other form, which is its dual, will become its min. Okay. So if it's a max function, the dual will become a min function. And if it is a min function, then it will become max function. I'm just writing it, you should write it, you can write it by Z also, but if you're getting confused, you can use a different objective function sign. So if it is a max function, convert it to a min function. If it is a min function, convert it to a max function. And in order to go ahead and convert that, you have to see that if you are converting it into a min function should always have everything greater than equal to 0. And a max function should always have everything in less than equal to 0. Let's now check this out. So now I have to do this for this function that I have created in the canonical format. So from here, I will take it forward. Because my objective function is a max function, when I will write its dual, it will be a min function. So let's write its dual down. So its dual will be a min function. I have converted my max to a min, max to a min. So when I'm converting max to a min, I will say that I have to now minimize this function. And whenever I convert max to a min, my constraint should all be greater than equal to. So I say max is equal to. Now, keep it here. My constraints have to be greater than equal to. So we will stop here. And we understand that whatever constraints we will have them greater than equal to with the max function. I will not write the function as of now. Just consider this as part of step 2, that when I go from the canonical format to the dual format, I want to convert my objective function. If it is max, I want to make it min. If it is min, I want to make it max. When I make it min, all signs should be less than equal to. When I make it max, all signs should be greater than equal to. This is it, that when I convert it to a max, less than equal to. When I convert it to a min, greater than equal to. That's it that I have to remember for now. Now, I will do the step 3 and I will come back to this point now. So third step, the number of variable in the primal will be the number of constraints in dual and vice versa. So basically what is happening, the number of constraints in the primal becomes the number of constraints in the dual and vice versa. Now, in order to understand this, we must know what is the number of variables represented by. So the number of variables are represented by n, and the number of constraints are represented by m. So if this is what is happening in the primal, when I go to the dual, then my number of variables will become m and my number of constraints will become n. This is how we will go ahead and we will write this thing. Okay. Now, so please understand this thing. When I talk about my variables initially, there are 3 variables, x1, x2 and x3. These are my variables that I have. And there are 3 constraints also, constraint 1, constraint 2, constraint 3. So 3 variables, 3 constraints. So accordingly, I will go ahead and I will write the equation of my dual. So because there are 3 variables, but 3 constraints also in this case, I will say let, please write down, W lambda 1, lambda 2, lambda 3 be dual variables. Let lambda 1, lambda 2, lambda 3 be dual variables. I am introducing 3 variables because there are 3 constraints. If suppose I had one less constraint, suppose I didn't have this constraint, then I would have introduced only 2 variables, lambda 1 and lambda 2. But because I have 3 constraints, I am introducing 3 variables. Okay. So let lambda 1, lambda 2, lambda 3 be the dual variables. Now we will stop here again and go to step 4. So step 4. Please write down. There is a cost coefficient in objective function of primal will be RHS constant of constraints in the dual and vice versa. So basically, what are the cost coefficients? The cost coefficients are these. What are multiplied here? So, you know, my x1 is multiplied with 1, x2 with 2, x3 with 1. These are known as cost coefficients. And what are the right hand side of the constraint? 2, 6 and 6. So I am saying that these cost coefficients 1, 2 and 1 will now become the right hand side constraints, and these 2, 4, 2, 6 and 6, these will become your cost coefficients. So now we know my cost coefficients are 2, 6, 6. My variable is lambda 1, lambda 2, lambda 3. My constraint right hand sides are cost now. So 2, 1, 1. So I will have 2, 1, 1 here. So this much is clear to us. Okay. Now please write down the next step. 5th step. For formulating constraints, we consider transpose of matrix. Very important step. So for this case, whatever matrix is earlier given to you, if I have to formulate my matrix from here, my matrix would be 2, 1, minus 1, 2, minus 1, 5, 4, 1, 1. This will be my matrix. I will go ahead and I will transpose this matrix. And when I transpose this matrix, you know, row will become column, column will become row. So the transpose of this matrix will be 2, 1, minus 1, 2, minus 1, 5, 4, 1, 1. Right, isn't it? So you will go ahead and you will get this here. This will become here. This will come here. And this will come here. So now I will take these as it is. So from there, I will get 2, 2, 4, 2, minus 1, 1, minus 1, 5, 1. Notice here, first of all, before we go ahead, 2, 2, 4. So I have written 2, 2, 4 here. 1 minus 1, 1. So I have written, this will be 1, sorry. 1 minus 1, 1 here. Minus 1, 5, 1. So I've written minus 1, 5 here. Is this clear? So whatever initial problem I had, I have converted this. From that matrix, I converted it into a transpose matrix, and I just wrote this transpose matrix as it is here. Whatever matrix was the transposed matrix. Now each transpose matrix here, I will get lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. Plus. Here I already have a minus sign. So 1 is not required. 1 is not required. Plus. 1 is not required. 1 into lambda 1 is simply 1. So I will get plus. 1 is not required. So I will go ahead and I will get this equation. Is this making sense? So this is how we have been able to convert these equations. So this was 1 to 1, right? Okay. So then you will say lambda 1, lambda 2, lambda 3 greater than equal to 0. This is how we have gone ahead and done it. So please understand what is the process that we did. From the primal, if it is a min, you keep canonical into a min. If it is max, you keep canonical into max. Just that if it is min, it is greater than equal to 0. If it is max, it is less than equal to 0. From canonical, you convert to dual. So if it is min, you convert this to max. If it is max, you convert this to min. In order to convert it to max, all signs will come in less than equal to 0. If it is min, all signs will come greater than equal to 0. This is how you can do this conversion. Okay. Now, let's go ahead and let's consider another question so that we can understand how to do the method of how to do primal to dual. Write down a question and do it yourself, right? So the question that I'm giving you is this. You have a max function to maximize z is equal to x1 minus x2 plus 3x3 subject to your given constraints x1 plus x2 plus x3 less than equal to 10. The second constraint is 2x1 minus x3 less than equal to 2. The third constraint is 2x1 minus 2x2 plus 3x3 less than equal to 6. This is what is given to you. Now, first of all, and it's given x1, x2, x3 greater than equal to 0. So the first thing is we will convert this in the canonical format. So canonical, if it is max, it remains max. If it is min, it remains min. And because all of these are already less than 0, I have to do nothing. This is already in its canonical format. So in max, I want all the constraints to be less than 0. Here, all the constraints are already less than 0. So my canonical form simply remains the same. To maximize z is equal to x1 minus x2 plus 3x3. Subject to my constraints also remain the same. x1 plus x2 plus x3 less than equal to 10. Second is 2x1 minus x3 less than equal to 2. Third is 2x1 minus 2x2 plus 3x3 less than equal to 6. This is my canonical format. Nothing changes in this case. Now I will go ahead and write my dual. So in dual, if it is a max, it becomes min. If it is a min, it becomes max. So I will write min. Right. Now I will see the coefficients will become the cost, and the cost coefficients will become the coefficients on the right hand side. So what will I have? I will have the coefficients 10, 2, 6 here, and I will have the coefficients 1, minus 1, 3 here. These are the coefficients here, right? The coefficient is 1, minus 1, and 3. So this is what I will do. There are 3 constraints. So I will have 3 variables. So I will go ahead and introduce 3 variables. Let variables be lambda 1, lambda 2, and lambda 3. So I will have lambda 1, lambda 2, lambda 3. And because I have three variables, x1, x2, x3, I will have three constraints also that I will form. So I will write three constraints, and because I am minimizing my function, so when you go from min function, from a max function to a min function, all the constraints will be greater than equal to. So what I do is I write a greater than equal to sign everywhere. And now I am just going to transpose my initial matrix. So my initial matrix was 1, 1, 1. X1 had coefficient of 1, x2 0, x3 minus 1, x1 2, x2 minus 2, x3 3. And I will transpose this matrix and I will get 1, 1, 1, 1, 0, minus 1, 2, minus 2, and 3. So if I write this, I will get 1, 1, 1, 1, 0, minus 1, 2, minus 2, 3. This is what I am going to go ahead and get. And I will go ahead and multiply lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. So now you will just put plus everywhere. And minus will remain minus everywhere. And wherever 1 is there, 1 into lambda 1 is simply lambda 1. So you can remove those ones. Right? And whenever 0 is there, that's not part of the equation also. So this is your final answer that you will get. So this is the dual form of the primal. What is the dual form? The dual form says that you will minimize z is equal to 10 lambda 1 plus 2 lambda 2 plus 6 lambda 3 subject to lambda 1 plus 2 lambda 2 plus this is 2 yeah, sorry, please make this 2 here, and then I will have 1 1 1 2 0 1. Okay, so I just made this mistake. This is going to be 2. So lambda 1 plus 2 lambda 2 plus 2 lambda 3 greater than equal to 1. Lambda 1 minus 2 lambda 3 greater than equal to minus 1. Lambda 1 minus lambda 2 plus 3 lambda 3 greater than equal to 3. So this is going to be your final answer. Let's take more questions to solve it first. So write down another question. So again, you have to convert primal to dual. So the question is, you have to minimize z equal to 2x2 plus 5x3 subject to x1 plus x2 greater than equal to 2, 2x1 plus x2 minus 6x3 less than equal to 6, x1 minus x2 plus 3x3 equal to 4. x1, x2, x3 greater than equal to 0. This is what is given to you. Now please understand this thing. See, whenever, first of all, we'll start from the very beginning. See, whenever you have an equality in the equation, an inequality is not there, then an equality kind of equation can be converted into an unequal kind of equation by saying that there are two equations that exist, x1 minus x2 plus 3x3 less than equal to 4, x1 minus x2 plus 3x3 greater than equal to 4. So you will say that there is not one equation that exists, But in fact, there are two equations that exist. Now let's write down the canonical format for this. So canonical format basically is going to say that if it is a min function, then what do I want? For a min function, I want that everything in the constraint should be greater than equal to 0. So because I see here less than equal to 0 and I see here less than equal to 0, so I will have to work on those also. So writing the canonical format, first of all, because there are three variables, x1, x2 and x3, and here there are just two variables in my objective function. This means that x1 would have had a coefficient of 0. So I get z is equal to, I'm minimizing z, 0x1 plus 2x2 plus 5x3. And then I am saying subject to, and now the first equation is correct, x1 plus x2 greater than equal to 2. The second equation is incorrect, so I will multiply with -1 throughout. So minus 2x1 minus x2 plus 6x3 greater than equal to 6. The third equation is also incorrect. So I'm going to go ahead and multiply it with -1 throughout. So I'm going to get minus x1 plus x2 minus 3x3 greater than equal to -4. Fourth equation is correct, so I will keep it as it is. x1 minus x2 plus 3x3 greater than equal to 4. And I will get x1, x2, x3 greater than equal to 0. So I have got its canonical format. Now from the canonical format, I will form the dual. So in order to form the dual, what can we do? First of all, if it is a min, I will convert this to a max. So I will say maximize z. Then whatever coefficients are coming here, I will have those in my cost function. 2, 6, minus 4, 4. Since there are 4 constraints, I will now have 4 variables. So this will be my new function. Since there were 3 variables, now I will have 3 constraints, and the coefficients of the cost function will become the right hand side. So 0, 2 and 5. Since I am maximizing, therefore I know that all my signs would be, according to maxima function, which will be less than equal to 0, less than equal to, so less than equal to, less than equal to, less than equal to. Again, you have to refer to the same thing, that because it is maxima in the dual, it will be less than equal to here. So this is what we will follow. And then simple, you have to just transpose this matrix. So the initial matrix in x1, x2, x3 is 1, 1, 0, minus 2, minus 1, 6, minus 1, 1, minus 3, 1, minus 1, 3. So this is your initial matrix. And when you will find the transpose of this matrix, this is going to be 1, 1, 0, minus 2, minus 1, 6, minus 1, 1, minus 3, 1, minus 1, 3. And you will put this as it is. So you will get 1, minus 2, 1, minus 2, minus 1, 1. So 1, minus 2, minus 1, 1. Then you will get 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1. And then you will get 0, 6, minus 3, 3. So 0, 6, minus 3, 3. This is what you will go ahead and get. Lambda 1, lambda 2, lambda 3, lambda 4, lambda 1, lambda 2, lambda 3, lambda 4, lambda 1, lambda 2, lambda 3, lambda 4. And then wherever the sign is missing, just put in a plus sign. And this is it. So 1 into lambda 1 is this, 0 into lambda is just 0. So you can just clean this up a bit. Right? So this will be your final equation. This will be your final dual. So I hope this is making sense how we are converting primal to a dual. These are important equations, okay? Okay. Now, you know, there is another thing that you can go ahead and do here. So, you know, you could have also said that let, because you know you are able to see that lambda 1, lambda 3 minus lambda 4 is coming common. So you can say that let lambda 3 minus lambda 4 or lambda 4 minus lambda 3, whatever you want to take common. Let lambda 4 minus lambda 3, let this be lambda dash, lambda 5 dash, something like this, or lambda 3 dash. So if you do that, then your equations can be rewritten as lambda 1 minus 2 lambda 2 plus lambda 5 dash less than equal to 0. Your second equation will become lambda 1 minus lambda 2, and then this will become minus lambda 5 dash less than equal to 2, and your third equation will become minus 6 lambda 2, and then it will be plus 3 lambda 5 dash less than equal to 5, and your objective function will also change, 2 lambda 1 plus 6 lambda 2, and then you will get plus 4 lambda 5 dash. This will be your function. So now what you have done is you can always rewrite your function saying that lambda 4 minus lambda 3 is a new variable. And now your equation, because you know, see here, there were 4 variables but 3 equations, right? So in order to do that, now this is better. There are 3 variables, lambda 1, lambda 2, lambda 5 dash in 3 equations. So this is a better way of writing the primal and dual in this case. Okay. Now consider this question. This is IIT JAM question number 22. It says, let x1 star, x2 star, x3 star equal to be optimal solution of this problem. Then this is asking about the dual. So first of all, we will create the dual. So because here we have to minimize, it is a minimum function. First of all, I will form the canonical form. So min will remain min. So min of x1 plus 5, x2 plus 2, x3. And because I am converting this to a canonical format, we know that using the canonical format, we can always change the signs, right? So I will go ahead and I will say subject to all greater than signs. And because I'm changing the sign, it will become minus x1 plus x2 greater than equal to minus 1. x1 plus x2 plus x3 greater than equal to 3. x1, x2, x3 greater than equal to 0. So this is what I have gone ahead and I have done. I have converted from my primal to my canonical form, ensuring that if it is a min function, I have greater than equal to sign being intact. Now I will form a dual of this. So in order to form a dual of this, I'm going from my canonical to dual, which means that if it is min, I will be converting this to a max with all constraints less than equal to. So I'm going to convert this into a max with all signs less than equal to. And since there are 3 variables, I am going to have 3 equations now. And since there were 2 constraints, I will have 2 variables now. So minus lambda 1 plus lambda 3. And this will go ahead and become 1, 5, and sorry, not plus lambda 3, simply lambda 2. I'm so sorry. This will become 1, 5, and 2. And then I will just create a matrix first. So this will be -1, 1, and I will have 0, and I will have 1, 1, and 1. And the transpose of this matrix is going to be -1, 1, 0, 1, 1, 1. So I will get here -1, 1, 1, 1, 0, 1. So if I go ahead and I convert this, this is going to be lambda 1, lambda 2, lambda 1, lambda 2, lambda 1, lambda 2. And then I'm going to just go ahead and put a plus sign everywhere. And as we just know that we can just remove ones, because 1 into lambda 1 is simply lambda 1. And I can simply say that, you know, this is going to go. So this is how my equations are going to look like. Now, after I have converted this here also, yeah, I'll get a 3 here, right? So -1 and 3. So -1 and 3 will come here. Now, after I have solved for this, this becomes my dual. Now I just want to find out what is going to be the optimum relationship or optimal solution of the dual. So now it's very simple. I just have to maximize this equation subject to these constraints. There are 3 constraints that I have. I have to find what is the maximum value of this equation with this constraint. So what am I going to go ahead and do? Well, I am going to simply go ahead and plot these lines. So when I plot the first line, this says minus lambda 1 plus lambda 2 is equal to 1. So if I have to plot this, then, you know, let's say that I take lambda 1 here and I take lambda 2 here. Then I am saying that lambda 2 is 1 plus lambda 1. So when lambda 1 is 0, lambda 2 is 1. When lambda 1 is 1, this becomes 2 and so on. So this is the equation that we are looking at. When this is 2, then this is 3, then this is 3, then this is 4. And, you know, if I see it with inequality, then minus lambda 1 plus lambda 2 less than equal to 1. Put 0 everywhere, less than equal to 1, 0 less than equal to 1. This is a false statement, isn't it? So you will get away from the origin. So your highlighted or shaded area will be away from the origin, like this. This will be your shaded area. Now let's go ahead and take this forward. So the next equation is lambda 1 plus lambda 2 equal to 5. Don't worry about inequalities first. Just worry about the equations. So when lambda 1 is 5, lambda 2 is 0. And when lambda 2 is 0, lambda 2 is 5. So I will go ahead and I will take this as 4 and 5 and 5. And I am going to just go ahead and mark these 2 lines here. And now I'm going to, you know, you can also find where will these 2 lines meet with each other. So, you know, if your first line is minus lambda 1 plus lambda 2 equal to 1, and your second line is lambda 1 plus lambda 2 equal to 5, you can solve these 2 lines simultaneously. And you will get, if I add the 2 lines, if I add the 2 equations together, I get 2 lambda 2 is equal to 6. So lambda 2 is 3 and lambda 1 will become 5 minus 3, which will be 2. So the point of intersection of these 2 lines will be exactly this, 2, 3. Okay. Now again, I will put zeros here. So 0 plus 0, which is 0, is less than 5. This is a true statement. So because it is true, I will shade region towards the origin. Okay. And now I will see the third equation, lambda 2 equal to 2, I will plot. So lambda 2 equal to 2 is going to be this equation. And then because I will put 0 less than equal to 2, this is a true statement. So I will shade towards the origin for this one also. So when I shade towards the origin, I will get this. So for all these 3 equations, the common region for first also, I'm so sorry. For this one, 0 plus 0 less than 1, this is true only, na? So if it is true, I will shade towards the origin for this one also. Towards the origin for this one also. So if we see the common region that we will get will be this. This will come out to be the common region. For all of them, you will shade towards the origin and this will be your common region. So you just have to put 0 and check. If it is true, it's true, I'm so sorry. If it is true, you will shade towards the origin, otherwise you will shade away from the origin, okay? So now what you will do is you are going to go ahead and you're going to, now because you have to maximize minus lambda plus 3 lambda 2, so that's what I'm going to maximize. So I have to maximize minus lambda 1 plus 3 lambda 2. Now what I will do is I will see where is this getting maximum, okay? So I have a lot of points with me. All these points are towards the origin. I mean, these are all the points, but make sure that lambda 1 plus lambda 2 has to be greater than 0. So it can only be in the first quadrant. Now the points that I can take is this. So I can take 0, 0. This is the first point. I can take this point, which is 5, 0. I can take the intersection of these two curves, right? So this equation was, it was lambda 2 is equal to 1 plus lambda 1. And because I'm equating it with lambda 2 equal to 2, so this point of intersection is going to be 1, 2. And this point of intersection that we see here, because I am intersecting lambda 1 plus lambda 2 equal to 5 and lambda 2 equal to 2, this point of intersection is going to be 3, 2. So for each of this point, I just have to evaluate this function. So if I evaluate this function at 0, 0, I will get 0. If I evaluate it at 5, 0, I will get minus 5. If I evaluate it at 1, 2, I will get minus 1 plus 3 into 2, 6, which is 5. And if I evaluate it at 3, 2, I will get minus 3 plus 3 into 2. I'm just putting it at each point here. Okay, so minus 3 plus 6, I will get 3. So which means my function is getting maximized at this point, which is 1, 2. So my function maximized when lambda 1 is equal to 1 and lambda 2 is equal to 2. So the relationship that they have is lambda 2 is twice lambda 1. So lambda 2 is twice of lambda 1. So the answer is B. Okay. This is how you can go ahead and solve this question. Thank you.